Okay, thanks. Yeah, hi again. So yeah, I'm going to talk a bit about apprenticeship learning. This is joint work with Liu Yang, Gongju Wang, and Yulun Song. So yeah, imagine we design a Mars rover. Its job is to drive around on Mars, collecting samples, doing various experiments. And we want it to be able to drive from place to place autonomously. And let's say it's already learned some reasonable driving skills, maybe even knows how to drive around rocks and that sort of thing. But we also want it to be careful because sometimes it gets into new situations where it isn't quite sure what to do, and it could be pretty dangerous if it isn't careful. So, what we really want is if it gets into a situation where it's uncertain about how to handle it, it sends a message to Earth and requests a human to take control for a bit. And the human replies with some instructions on what to do. And the rover follows those instructions and continues on from there. And on top of this, we also want it to learn from this interaction. So it can sort of better identify the appropriate actions in the future. I'll let him leave. OK. All right, so we're going to formalize this as essentially an MDP kind of setup. So there's a state space, and there's an action space. These are just arbitrary non-empty sets. There's a policy class, which is just a set of functions mapping states to actions. There's some unknown target policy pi star in the class. And there's an unknown environment, P, and that consists of an initial state distribution and a state transition distribution, which just says if you do an action in a certain state, what's the distribution over the next state? In the learning protocol, you have the initial state sampled from the initial state distribution. Then it goes in rounds. On each round, the learning algorithm observes the current state, ST. It can then optionally query an oracle, which tells it the optimal action, the target policy's pi star of ST action, and then it takes that action. Let's say AT is the action that it takes, so its AT is equal to pi star of ST in the case it queries. Otherwise, if it chooses not to query, then it can choose whatever action it wants, any action AT in the set of actions. And in any case, we then get our next state sampled from the state transition distribution, given that we did action AT in state ST. The guarantee we're going to require is a reliability requirement. So we'll require the algorithm to guarantee that in every state, it's always doing the optimal action. This is in the realizable setup. We'll talk about some relaxations of this later. And then subject to this guarantee, we're interested in what is the optimal number of queries that such an algorithm must make. And so we analyze this in a kind of minimax, like best algorithm, worst environment number of queries. OK, so in the realizable case, we get actually a fairly exact answer to this. I mean, an exact answer to this. We find that the optimal query complexity is exactly the eluder dimension. Of course, we're never larger than the time horizon t, but otherwise, the eluder dimension is the exact answer to how many queries you have to make. The eluder dimension is a quantity that comes up in reinforcement learning and contextual bandits. It's defined like this. So it's the maximum n such that there's a sequence of n state policy pairs, Si pi I, such that for each I, the policy pi I agrees with pi star on the whole prefix up to but not including time I, and then it disagrees at time I. So it's correct on the prefix but disagrees on the next point. That's the eluder dimension. And I can give the proof. It's a fairly simple proof that the eluder dimension exactly characterizes the optimal query complexity. For the lower bound, let's just set up an environment that just follows the sequence of states in the eluder sequence. Then notice that any algorithm that's reliable must query at every time, because like if there were some ST where it tries to guess pi star of ST, either it guesses wrong what pi star is, or it guesses pi star, and then it would be wrong. It would be unreliable in this alternative environment where pi t, the one that flips that one, that agrees with pi star up to that time, but flips that one to some other action, like disagrees on that one state. So it has to be reliable for all possible targets, and so it would be unreliable for pi t if it were to guess pi star. So it has to query every time. In the other direction, we use this classic strategy called disagreement-based learning, and this is something introduced by Kahn, Atlas, and Ladner, and we call it CAL as a tribute to them. So so let's introduce some notation. So for any set of policies V, the region of disagreement of V, which we denote dis of V, is the set of states such that there exist two policies in V that disagree on what action to take in that state. Then the CAL algorithm is defined like this. So we initialize the set V to the set of all policies. And then on each round, if the state is in the region of disagreement of V, then we go ahead and query for the optimal action, and we take that action. And then we update the set V to be the set of all policies in V that agree with that optimal action. And so inductively, this maintains that pi star is always in the set V. And that way, in the other case, where the state is not in the region of disagreement, we can just take the action that all policies in V agree on, and we know since pi star is in V that this will be the pi star action. So this is definitely a reliable algorithm. Then for bounding the number of queries by the eluder dimension, just notice that the sequence of queries is an eluder sequence, right? So each time that we're querying, it means that there's some policy that's survived, that's still in V, so it agreed with all of the queried actions so far, and yet it disagrees on that next state ST, and so that's the definition of an eluder sequence. So that the number of queries is at most the eluder dimension. Okay, so that was the realizable case, pretty straightforward. We also study noisy oracles in this work, and we formulate that by augmenting the environment to also have an oracle response distribution. That's just a distribution over actions given a state. And we'll assume that it's what we call a preferential noisy oracle, which just means that the probability of the pi star action is a little higher than the probability of any other action from each state. In this setting, the formulation is similar to before. We have an initial state drawn from the initial state distribution. It goes in rounds. On each round, the algorithm observes the state ST. It can optionally query, which in this case means it's going to get a sample from the oracle response distribution given the state ST, and then it just takes the action that was given to it by this sample. Otherwise, if it chooses not to query, then it can choose any action AT at once. And then in any case, we sample the next state from the state transition distribution given that we did action AT in state ST. In this case, we slightly relax the reliability requirement. And we just require that with high probability, in every state that it doesn't query, it takes the optimal action. Right? So if we did query, we just take whatever action it told us. But if we don't query, then we need to guarantee we're taking the optimal action. So we have an algorithm that is reliable under preferential noisy oracles. And it's again based on the disagreement-based principle. So we initialize again a set V by the set of all policies. We have a set Q, which is going to be the set of queries. And then at each round, if the state is not in the region of disagreement, then we'll take the action that's agreed upon by all of these policies in V, and we'll again inductively maintain that pi star is in V, so this is guaranteed to be reliable. And otherwise, if it's in the region of disagreement, then we query, so we get this sample action from the Oracle response distribution, and we just add that state and action to the set of queries Q, and then we update the set V using, again, a principle that shows up in a lot of work on disagreement-based learning. Basically, let pi hat be the policy that's in V that agrees with the most actions from the Oracle so far, and then we keep in V all of the policies that don't disagree with the action too much more than pi hat does, where too much more is quantified by a kind of Bernstein inequality. And by a kind of familiar route, we're able to show this is reliable under preferential noisy oracles. The only thing we have to be careful of is, we don't have IID samples here, but it turns out that you can get like a uniform Bernstein inequality that's sufficient for us using martingale difference concentration inequalities. To get a quantitative query complexity bound, we need to introduce some kind of parameterization of how noisy the Oracle response distribution is. We look at two versions of this in the paper. The simplest one is the Massart noise assumption. So this is just that the probability of the pi star action is bigger than the probability of any other action by at least some delta margin, so some gap. And then we show the optimal query complexity here is again characterized by the eluder dimension, but also a 1 over the square of the gap term, and then some log factors as well. We also study a sort of Sibikov noise kind of condition in the paper, which is itself kind of interesting because so Sibikov noise, usually we think of it as the frequency of getting a state such that the action distribution is particularly noisy is low. So the frequency of a high noise action is low, but like that frequency has to be under some measure, and formulating like what measure would be appropriate here in an MDP is not so straightforward, but we find an appropriate formulation in the paper, at least for the purpose of this reliable apprenticeship learning. Improving the query complexity bounds, again, we're sort of following a familiar route, just replacing IID concentration inequalities by martingale difference sequence concentration inequalities. But there's a key lemma that allows us to introduce the eluder dimension to that analysis. And I think actually this is maybe one of the most interesting technical contributions of the work. So the lemma says that for any k and n, if you have a sequence of n states such that for all states in the sequence, the SI is in the region of disagreement of the set of policies that make at most k mistakes so far on the prefix of the sequence, then the length of that sequence can be at most k plus 1 times the eluder dimension. I find this kind of interesting because you can view it as analogous to a known result from the analysis of disagreement-based pack learning, where there's this inequality that the disagreement coefficient is bounded by the star number. And here we can view this as that an online disagreement coefficient is bounded by the eluder dimension. That's sort of, if you read it and look at these two theorems together, it has that analogy. Okay, thanks.
I have time for some questions. Okay, can somebody?
Have you considered a model where the policies output distributions over actions as opposed to deterministic? Like, do you know if anything would change? And
where the policies themselves, no, we didn't consider it. Yeah, I mean, I guess the question would be how to formulate reliability in that setting. Yeah, we haven't thought about it.
Kind of same. Have you considered settings where, in addition to actions, you have like value, like reward or utility, and you get some approximation? Let's say you get a factor of 2 approximation to the best utility action, and you want to not get the best action every time, but get close to the value. Would things be similar? Things be different?
Yeah, it's a good setting to think about. We did think a bit about if there are rewards and somehow there's an oracle telling you some information about rewards, but not exactly the right action. We found it hard to formulate, basically. But yeah, for sure, it's an interesting question to consider if yeah, somehow we're not getting as much information about actions, but more about rewards.
Maybe I'll ask one. Can you say something about the proof of the Q lemma?
The proof of the lemma. Yeah, I certainly can. Thank you for asking. So, the lemma is actually has a pretty cool proof. So, essentially, what we're going to do is build the eluder sequence, build an eluder sequence based on that sequence of S's. So let's say Z is the initial sequence of S's, and we'll initialize an eluder sequence to empty, and we're going to build the eluder sequence in reverse order from the last to first. And basically, you just take the last element in Z, and you know, there is some policy that disagrees with pi star, and at most k previous elements of Z. So let's add that policy and state to the beginning of the eluder sequence, and remove from Z all of the states that it's wrong on. There's only k other states that it's wrong on. And so what you end up with is pi is correct on everything that's left in Z. And then so inductively, you keep adding these states and policies that are where the policy is correct in the whole prefix, but wrong on S. And so sort of in reverse order, we're building this eluder sequence. And then notice that just for each element that we add to this eluder sequence, we're only removing k+1 elements from Z. And so the length of the eluder sequence is at least the length of the initial Z divided by k+1.
Thanks very much. Let's thank the speaker again.